Hi and welcome back folks. So today we'll be studying about fields, and in the last lecture we looked at equality of sets, and over there I explained a bit of a very complicated concept of these um, non-unique null sets, but I hope you understand that. If you have any doubts, please do feel free to post them in the comments. I'll be happy to answer them to the best of my ability. And now moving on to the fields. So fields is a collection of sets or events, and that collection of sets is called a field if and only if it satisfies two conditions. One is for all A belonging to F, that is all sets A belonging to the collection F, the complement of A, that is A bar, must also belong to F. Okay, simple as that. If A is there, so is A bar. They come in pairs. And if AB, there are two sets AB belonging to the collection, and in that case A union B must also belong to the collection as well. So if you have A and B, then you must have A union B as well. It's a must. And so with these two conditions itself, you have you can call any collection of sets as a field. And as I was explaining, in the probability space omega fp, that f over there is a field. It must be a field. Alright, so the collection of subsets that we have, it forms a field. Okay, so some important properties of fields that I want to highlight is that for all A and B that belong to the field, A intersection B must also belong to the field. Alright, that's simple to prove. If A and B belong to the field, then A bar and B bar will as well. That means A bar union B bar, which is AB whole bar, De Morgan's laws. And with this we have proved that AB also belongs to F. Alright, so all of these things are from these two properties only. Okay, next is omega and phi, that is the certain event and the impossible event phi. They are also members of the field, and this phi represents the null set. Okay, and okay, from henceforth I am not going to uh, consider all these events which have zero measure. If I do, I'll mention that, and we'll deal with that appropriately as well, although it won't make much of a difference. But just to avoid confusion, this phi over here represents the event with which is an empty set. Alright, okay, now omega and phi, they are also members of F, and that means that A belongs to F, that means A bar also belongs to F. Hence the union and intersection of the two will also be a member of the field. So the second part actually came from the previous lemma. I used that. Alright, now that we are a bit more familiar with the concept of fields, now we have something called a Borel field. Now Borel field is also a field only, but in that field, if we have an infinite sequence of sets that belong to that field, then their union, their infinite union and infinite intersection is also an event in F. Alright, so if you have a sequence of sets like this or events, then A1, A2, An, all of them are members of your field. Then that would mean for a Borel field, the infinite union and the infinite intersection, they are also members of F. So this and this, these two operations, they yield a set as well, and they also belong to F, and this is valid for any sequence of sets we choose. Alright, so if we can prove this, then we have ourselves a Borel field. Now what's the significance of this? I mean, any normal field would have sufficed. Why do we have to unnecessarily complicate and add in this Borel field? Alright, so we use a Borel field because this thing is useful in some examples when we want to find the union of infinite events. So if a1, a2, etc. is a sequence of mutually exclusive events. Okay, so we have a sequence of mutually exclusive events. Oops. So by the virtue of f being a Borel field, this union, this countably infinite union will also be a event, and that would mean the probability of this infinite union, I can write it as a limit as n tends to infinity of the finite union I equals 1 till n. So the limit as n tends to infinity, that will be the probability of the infinite union. And now since AIs are mutually exclusive, so I can write this term over here as a summation of the individual probabilities. Now the limit, oops, I forgot to write n tends to infinity. Okay. Now as n tends to infinity, the limit of this summation will approach I equals 1 to infinity of the individual probabilities. That's that whole summation of individual probabilities of each of the events in the sequence. Now this infinite summation thing would only be valid if this sort of event even existed. So if the countably infinite union, if it was even possible for all sequence, then only this probability would exist. That's when I would even be able to proceed with the next three steps. So that's what Borel fields are all about. Let's see this put into action. Okay, now say you flip a coin until you get a heads. So let's say you have all the time in the world and you're flipping a coin and you keep on flipping it until you get a heads. That's when the game ends. Now find the probability of requiring more than k tosses. Now k is some number from 1 to as much as you want. Let's say k is 10, 20, something like that. So what is the probability that you will require more than 10 tosses? Alright, so the solution is that we consider xi as the event where the game ends after I tosses. That means I minus 1 tails and 1 head. That will occur at the last. Okay, so the probability of xi happening is 1 minus p raised to I minus 1, that is for the I minus 1 tails, times p. So p is the last heads. So I'm considering the probability of heads as probability of heads is p and probability of tails is 1 minus p. Okay, cool. Now for each xi we have found out its probability. Now a, let's call a as the event that the game requires more than k tosses. So that means that would be the union of xk plus 1, xk plus 2, all the way till infinity. So this is also a countably infinite union. It starts from k plus 1, goes till infinity. And note that all the xi's are disjoint. So if you require k plus 1 tosses, you would land the event xk plus 1, but the game would end. It does not mean that you would also land xk plus 2 or xk plus 3, something else like that. No, that won't happen. If you land one event xi, all the other possible xi's, x1, x2, x3, whatever that is, you won't land any of those. You can only be at you can only end the game at one of these events. That's why they're all disjoint, and this would allow me to call upon the result that we saw before. So p of a is basically the summation of p of xi. I'll write that down as well. I'm getting a bit lazy when it comes to writing steps these days. This is the summation I equal to k plus 1 to infinity p of xi. Alright, beautiful. Now that would be the summation of all of this, which, if you remember your geometric series pretty well, would evaluate to 1 minus p raised to k. Alright, so we could we could actually do this sort of thing, call this an event. Well, because the subset of events in this case would form a Borel field. Now, I'm not going to prove that they form a Borel field. For in this case, just take it for granted actually. But with that, I illustrated what's the power of these sort of things, why Borel fields are important, and we'll also see that uh, the probability space omega fp, in that f will actually be a Borel field over the subsets of omega, and I'll tell you the implications of that later. But for now, uh, thank you, have a nice day, stay tuned.